The next talk is provided by the Norihisa Fujita from University of Tokyo. University of Tsukuba, my colleague. And do I need to introduce? Yeah. Please stop the sharing. So there, just for the okay. So, and I will very briefly introduce Fujita-san. And he's an assistant professor at the University of Tsukuba Center for Computational Sciences now. And he got PhD degree from University of Tsukuba in 2016. Actually, he was my ex-student. And he, from April 2016 to October 2019, he was a postdoc researcher on the Center for Computational Sciences. And he's now the assistant professor there. And his research interests including the high-performance computing, accelerators, system architecture, high-speed networks, reconfigurable architecture, and system software. So he's doing almost everything about the system software. And he's a member of IEEE and IPSC. So today's his talk is titled Performance Evaluation of the System Allocated Memory on NVIDIA GH200, which is running here in the Kashiwa campus of the University of Tokyo under the JCAHPC operation. Okay, please go ahead.
Okay, thank you for introduction. And okay, so that I will talk about the performance evaluation of the new unified memory of the NVIDIA Grasshopper superchip. So I will also talking about the MPI communication performance of on the MIYAVI supercomputer, but I will focus on the system allocated memory and the new unified memory with the communications. So that the basic performance is already shown by the Professor DK Panda, but I'm focused on the unified memory and the communication performance. Yeah, so that as you know, so far, the GPU and the CPU have been independent processor, so that the GPU and the CPU have their own isolated memories for each other. So that this architecture making some challenges, including programming models. So so we have to manage the data transfer and the memory allocation for each CPU and the GPU. So that we consider that the GPU programming is very difficult because of the separated memory. So recently, the NVIDIA and AMD have a high performance advanced architecture, including the NVIDIA GH200 Grasshopper superchip, which is on that system, the CPU and the GPU are tightly coupled on top of the single module. And also they are connected by the high speed and the low latency proprietary bus named NVLink C2C. And also so that as you know, we are now starting the operation of the MIYAVI supercomputer equipped with the GH200 superchips. So in this talk, I will talk about some performance evaluation result of the unified memory systems of the GH200. So GH200 introduced a new unified memory. However, the performance has not been well studied, I think. And also compared to the previous generations, I mean some traditional system connecting the PCI Express, the new GH200 unified memory has a lower overhead and higher bandwidth, of the data transfer between CPU and the GPUs. And also I will talk about the performance of the MPI communications. I mean, especially the communication performance on the UN if the data is located on the GPU memory. So that there are some existing related works about the GH200 memory system performance evaluations. So Safai and evaluated some fundamental performance using the Rodinier and the QC simulation benchmarks. So In addition to that, we compare the communication performance on the actual supercomputers on the MIBG systems. So this figure shows an overview of the GH200, and some figures and the pictures are cited from the NVIDIA official papers. So that as you can see, in the GH200 is a big module containing a CPU and GPU. So the left-hand bigger module is a Grace ARM CPU, and the right module is a Hopper, NVIDIA Hopper GPUs with equipping with HBM3 memory. So, however, still CPU memory and the GPU memory are separated. So the CPU has LPDDR5X memory with a capacity of 120 gigabytes, and the GPU has HBM3 memory, and the capacity is 96 gigabytes in the MIBG systems. This architecture is different from the AMD APUs. So in the AMD case, the GPU and the CPU and the GPU share the same HBM memory, but in the Grace Hopper system, the memory still are separated. However, the cache coherence is maintained by the between the CPU and the GPU through the NVIDIA proprietary interconnect, as shown here. This is a NVIDIA proprietary interconnect bus, and connecting the CPU, GPU at very high bandwidth. So each direction has a 450 gigabyte per second and 900 gigabyte per second of bandwidth in total in bi-directions. Next I will talk about some detail performance number of each CPU and the GPUs. So the most important thing is that the CPU is ARM-based architectures. So the Grace CPU is ARM architecture. So if you want to run proprietary software, which depends on the x86 Intel architectures, you have to special support for them. And also the Grace CPU has a 128-bit SVE SIMD instructions and achieves 3.4 teraflops at 3 gigahertz. And the number of the core is 72, and the memory is, as I told you, but 120 gigabyte of capacity and 512 gigabyte per second of the bandwidth. The Hopper GPU is based on the H100 GPUs, so that I believe that some of you are already familiar with these types of the GPUs. So the H100 Hopper GPU have 67 teraflops in the double precision, and the memory is HBM3, and the bandwidth is 4 terabytes per second. So that the same core are used with already existing NVIDIA H100 GPUs, so that you can run the same CUDA or OpenCC applications without any change on our new supercomputers. However, the interconnection between the CPU and the GPU is different, so that you may feel that very faster data transfer between the CPU and the GPU compared to the PCI Express traditional connections. And next, I will talk about a new unified memory called system allocated memory, or SAM for short. In the GH200 system, the GPU and the CPU share the same address space, and cache coherence is maintained between the two processors. And they are treated as a NUMA node in the Linux kernel. So the CPU is a NUMA node 0 and the GPU is a NUMA node 1. And however, the memory characteristics is completely different in each NUMA domain. This is the most this is different from the traditional CPU NUMA systems. So the CPU, the Grace CPU has a very low latency memory, but the Hopper GPU has a higher latency but higher bandwidth memories. So in this system, the system system allocated memory, some is normally or the regularly allocated memory. Normally regularly means that some memory allocation using for example, the malloc function in the C or new operator in the C++ or allocate in the Fortran. So in some memory, and both CPU and the GPU can access the data, and the cache coherence is maintained between the two processors. And also the memory migration is supported by the memory system. Supported by the hardware. So the memory pages are allocated by the fast touch policy. And this is, I think that this is the same policy as the CPU NUMA systems. And also the memory migration is happened on the memory access from the GPU. Currently, we observe that this migration is only happen from the CPU to GPU, one direction. Migration is observed. Opposite direction is not observed yet. Anyway, you can still use the CUDA API as the same way as the traditional PCX environment. So you basically you don't need to change anything in your applications, CUDA code or OpenACC code. So this is a summary of the system allocated memory. So in the grasshopper system, the page size is 64 kilobyte, and is used. And this table shows access permission from the GPU and the CPU. So the traditional way is fixed allocation and no migration is happened. For example, you use the memory allocation by the CUDA malloc, CUDA API. This memory is located on the GPU, and migration never happens. And also the CPU cannot access to this region. Now, of course, the GPU can access the CUDA malloc memory regions. And also, if you allocate the memory by CUDA malloc host function, this is also the CUDA API. With this function, the memory is located on the CPU memory, LPDDR5X, and the migration never happens, but both CPU and the GPU can access to this memory. For some allocation, you can use any kind of the memory allocation API, including the malloc or calloc or something like that. In this case, the memory location is determined based on the fast touch policy, and the migration is supported. And also the CPU and the GPU both can access the data region of the allocated by these functions. So also the GH200 support the page migration for the some allocations. When GPU access the page, memory page on the CPU, and also the page is allocated by some allocations, the page may be migrated to the GPU. So that according to the NVIDIA documentation, each page has some counters, and the migration will happen in certain conditions. And the single access to the CPU memory is not enough to activate the page migration. Multiple memory access are required to activate the memory page migration. Anyway, this migration is automatically performed by the system. So the GH200 automatically moves the data between the CPU memory and the GPU memory. So application don't do anything for this migration. After the data is migrated, the memory bandwidth is improved from this condition to the HBM3 conditions. So next access will be faster. And also, as I said, the opposite direction, from GPU to CPU migration is not observed. So you don't need to worry about the opposite direction of the migration. So in this evaluation, we use the MiyaBG supercomputer located in here center, and you can see this system after this seminar. So I will skip the detail, but MiyaBG equipped with more than 1,000 of the GH200 nodes and achieving the 78 petaflops from the GPUs. So the next I will talk about some memory performance of the system allocated memory using the memory copy benchmark with a wide variety of parameters, how to memory allocate and the memory page location, and who copies the data and what API used for the data copy. And also for the system allocated memory, fast touch is performed before the benchmark, before the running the benchmark to ensure the entire array is located either LPDDR CPU memory or HBM3 CPU memory. So this is the fundamental performance of the GH200 NVIDIA performance. So this figure shows the data copy performance using the CUDA API. I mean the CUDA memcopy variants. And this is the performance with the traditional ways, and no system allocated memory used. So the CUDA malloc function and the CUDA memcopy function is used. So here you can see some performance numbers. The host to device memory copy is up to 400 gigabytes per second, and device to host is up to the 300 gigabytes per second. So this is in this case we used only one CUDA stream, and so if you multiplex some data copies in parallel, performance will be better. But anyway, this performance is much faster than the PCI Express bus, and around 7 times faster than the PCI Express. Next is the memory performance of the local memory. Local memory means that the LPDDR memory for the CPU and HBM memory for the GPU. So as you can see, for the memory, for the CPU memory, we can achieve around 400 gigabytes per second memory access performance. And faster performance is observed on the small cases, but this is affected by the cache. So the actual memory bandwidth performance is around 400 gigabytes per second for the CPU memory. And the same and also for the GPU memory bandwidth, we observed around 3.4 terabytes per second performance. And no performance fluctuations was observed, and the performance is very stable for each size in the GPU memory. So as and also as I told said before, the NVIDIA C2C has 400 gigabytes of the memory bandwidth. So from the CPU perspective, we can say that LPDDR5X and HBM3 have the same performance order. So that you don't want from the CPU perspective, you don't need to take care about the location of the data either on the CPU memory or on the GPU memory. Next, I will talk about some performance of the page migrations using using the memory copy benchmark. So initially we in this benchmark we have the two arrays A and B. So initially, all pages of the array A and array B are located on the CPU memory. And then the GPU copies the data between the array A and array B. Initially, the all data is located on the CPU memory. So this is a very inefficient condition. So the LPDDR5 to LPDDR5 copy is performed by the GPU, achieving the lower performance. So in the median, after some migration happened, some elements of the array A and array B are migrated to GPU memory. So in this case, some data copy is performed between the LPDDR-X still. However, some copy are performed between the HBM3 memory. So in this phase, the performance is gradually improving. After the all elements are migrated to GPU memory, this is the fastest case because all data copies performed between HBM3 to HBM3. This figure shows the migration performance evaluation result. We performed the memory copy benchmark with multiple times from up to the 200 times. And also we executed the same benchmark 10 times to check the variance of the performance. So that each line shows one try of the running the benchmark. At the beginning, the data is located on the CPU memory so that the performance is very low. However, the performance is improved over iterations. And thanks to the automatic data migration between the CPU and the GPU memory, the performance is getting the better and close to the CUDA-Malloc native performance. However, as you can see, the performance after the migration has completed is worse than the native access. In the native access, we can achieve the 3.4 terabyte, but in this case, we achieve that 3.0 or 3.1 terabyte per second, so a little bit lower performance due to the overhead of the page migrations. This figure shows the page migration performance on the various state size. As you can see, the array size is changing from the 128 megabyte to the 32 gigabyte. So as you can see, the time to migrate is time rate for the compression is roughly proportional to the array size. And also you can note that in the large array, for example, the 80 gigabytes case, the pink line, performance after the migration is very bad, is worse than the small cases. I believe that this performance degradation is happened by the GPU side TLV misses. So that we have to compare the performance using the huge pages. So that next, this figure shows that performance comparison of the Himeno benchmark. Himeno benchmark is a Poisson equation solved by using the Jacobi iterative method, and this benchmark is memory bandwidth span. So we apply the system allocated memory to this benchmark and compare the performance on the MIAB J200, and the Pegasus is a different system with PCI Express of the H100 GPUs. Yes, as a result, some implementation performance is underperformed by the traditional implementations, includes the traditional unified memory. I think that this is affected by the lower memory boundaries of some memory shown in the previous page. And however, we believe that the advantage of the sum programming model is the non-management is required anymore. So if you use the system allocated memory and OpenCC, we can program the GPUs with the same complexity as the OpenMP CPU. So you don't need to manage the data location or data transfer between the CPU and GPU. You can just you have to write some OpenCC parallel directives to run your application on the GPUs. Next, I will talk about some communication performance result using the MPI. So traditionally, the NVIDIA provides a GPU direct or GDR for the direct communication between the GPUs in the different node. However, GPU assumes the GPU memory is isolated from the CPU and which is located on over the PCI Express. So we performed some experiments on the MPI communications. We found that GPU direct is no longer used for the some memory data transfers. So the next I will talk about some background information of the MPI. So the some MPI application, MPI implementation using the Unified Communication X library or UCX library as a communication backend library. So in the such MPI implementations, communication capability and characteristics are based from the UCX. So in this case, if UCX can handle the some data transfer efficiently, MPI can handle the some memory data transfers. And also the NVIDIA InfiniBand supports some memory using the on-demand paging mechanisms to accelerate the data transfer. So if the ODP enables the memory data is keeping on the GP memory while the communication happens. Otherwise, without ODP, page move to the CPU while the communicating. We believe that this behavior is not desirable in GH200 architectures, so that to obtain the best communication performance of the MIBG system, you have to enable the ODP feature on the InfiniBand. Unfortunately, the UCX already supports the ODP, and you can change some behavior using this environment variable, UCX reg non-block mem types environment variable. So this ODP configuration is enabled by default after the UCX version 1.17. And also this library installed on the MIBG system, so that if you use MPI on the MIBG system, that this ODP is enabled at default. So and also I will show some benchmark performance evaluation results from the using the OSB bandwidth benchmark from the DK's the OSB benchmark. I compare the three patterns for the performance evaluations: CPU, GPU sum ODP, and GPU GDR. So ODP is enabled for the CPU memory and the GPU memory. And also the GPU GDR is a traditional way for the GPU direct communication not using the system allocated memory, using the CUDA mark API for the fixed memory allocations. This figure shows the communication performance of the on the different two nodes on the MIBG systems. So the difference of the three methods is very small, so you cannot see it's difficult to see the difference between among the three lines. So that I show the relative performance to the CPU in the right bottom figure. So this is the relative performance of the CPU memory. So that if and also this figure shows that the GPU GDR is not so fast on the GH200. So GPU GDR is 10% slower than the GPU system allocated memories. I believe that this is some UCX has some overhead to manage the GPU direct regions. So the GDR requires some special memory management for inside the communication library. So I believe that this overhead decreases the performance on the short message transfers. And also we found that the GPU sum is comparable performance to the CPU native memories. And also the much better performance on the small message sizes. Okay, let me conclude my talk. So that we evaluated the system allocated memory performance on the GH200 and the MIBG systems. So that NVLink C2C provides a fast communication between the CPU, GPU, while maintaining the cache coherence and providing us to the efficient data sharing between the CPU and the GPU. And also the internal communication, MPI communication, also shows a very good performance on the system allocated memory. The future work is we want to plan to apply the system allocated memory on the practical applications, and also we have to compare the performance with the AMD platforms, because the University of Tsukuba will have the MI300A supercomputers for the next April, I think.
Yes, February.
February. Okay. Okay, that's all. Thank you for listening.
Thank you, Mr. So is there any short question, comment? So Nani-san, this is some we need to care about the system memory, system allocated memory. That is a totally different system of the traditional PCI Express.
Yeah.
It's one. So that it isn't. We always thought that the GDR is best, almost best. But in this case, GDR is not so much good. About the 10% loss in the shorter message size. So I think one of the reasons is, of course, as like Fujita-san said, their overhead of their controlling the GDR mechanism. But also, I think in the GH200, PCI Express is on the mainly equipped on their Grace side, not on the GPU H100 side. And H100 can access to the PCI Express if it wants.
Yeah.
Through the NVLink C2C,
Yeah.
then CPU and the PCI Express. So the GDR is based on the idea that the GPU and the HCA are connected by the same PCI Express bus. So they are close. So that it is okay to have a RDMA directly skipping the CPU memory copy. But I think, I guess GH200 is totally a different situation.
Yeah. First of all, it would be better to see the latency, not bandwidth, for small message sizes. Could you go back to the previous slide, or maybe one? Yeah, this one. So for small message sizes like 100 bytes or 1 kilobytes, as you said, it's difficult to see the difference between these three. And also, as Professor Wok said, that the overhead is the main concern. And to see the effect of overhead on each implementations or in each communication method, we need to see the absolute value of latency. So I think the relative bandwidth is not enough. It's better to compare the absolute latencies. That's first comment. And another point is, my personal interest is invoking communication operations from GPU side, not CPU side. So currently, all applications call MPI functions from CPU side, but actually, NVIDIA's GPUs has a facility to call communication operations from GPU side. But I think because of the security reason, it's usually not enabled. And recently, but there are some techniques to kick. It's called doorbell technology. It kicks GPU kicks the CPU side to invoke the MPI library or communication. So it reduces the overhead of synchronization between CPU and GPU. So I'm interested in that kind of technology can improve the performance in GH200.
You mean that the GPU, if it is allowed, GPU can
directly input
without returning from the kernel to the GPU?
No. Yes, it's very old technique. I think it has been existing more than 5 years, maybe 10 years. It's called GPU direct async. And I saw NVIDIA once had the implementation, experimental implementation of GPU direct async, but I think it's stopped maybe because of the security issue, right? Maybe. Yeah.
I have a comment. So actually, in last year, so I heard such kind of a technology at the GTC, and the name was GPU initiation for the communication. But I can see still so available. So so another kind of technology for the actually for the file I/O. So they are struggling developing such kind of technology. So very similar, I think.
And also, I'm concerned that communication management is very complicated for the GPUs. And
And so, for example, ODP. So we need to enable ODP to make GPU direct happen, and so we can't rely on automatic migration while the communication is happening. So,
Okay, so how about continue the discussion, because this is a very interesting.
I have a comment. So I think the GPU Direct Async, there is a new support called InfiniBand GPU Direct Async, IBGDA. So that is the new feature. Whatever we are working with GPU Direct Async, it has got modified, enhanced. That is the latest support NVIDIA provides.
Thank you. Okay, so the
from the
oh, sorry, who?
Ota-san from list.
Okay, so please speak.
Oh, can you hear me?
Yes.
Okay. I have one short question. So on the last slide, so on the tilt miss issue, do you have any idea to avoid this sort of performance degrees using some standards or tuning techniques? I want to know.
Yes, so that huge pages is most fundamental technique
yes,
to avoid the TF misses, and I believe that huge pages is also supported on the GPU side, not only the CPU side.
So can you change the page size on your machine?
64 kilobyte for the regular pages.
So I have a comment. So actually, in MiaPG, the transparent huge pages
Enabled, yes.
enabled. And so huge pages are so very big. So with 512 megabyte.
Okay.
So very, very long time passed from the boot. So not
okay. I understand.
Fragment happens, so that we need to some compaction or such kind of
okay.
to reduce the fragment.
Yeah,
Okay.
THPs are very unstable.
I see. Okay, thank you very much.
Okay, thank you. Okay, so I'd like to just conclude this session, and maybe if you have any question, and we will continue in the open discussions session. Okay, thank you very much.